Greetings, fellow mathematicians. We're going to take a look at how to differentiate polynomials, which are one of the most important types of functions that you're going to be differentiating in your Calculus 1 course. Now, to put it simply, polynomials, they're just basically a bunch of powers of x multiplied by coefficients, multiplied by numbers. Now, how we differentiate polynomials is by combining several simpler, more basic differentiation rules, which you likely just learned right before this in your Calculus 1 course. So the four rules that we're going to combine all together: first, the derivative of a constant. The derivative of any constant is 0. Next, the power rule. The derivative of a power of x, x to the n. We bring the power n down front and then subtract 1 from the exponent. And the other two that we're going to need to basically combine these powers of x into a polynomial. Third, the constant multiple rule, which says if we are differentiating a constant c times some function of x, what we can do is bring the constant in front of the derivative, or pull that out front, and then just differentiate the function of x. And then we multiply that derivative back by the constant. All right, that's going to be how we deal with the coefficients in our polynomials when we eventually get to this example. The fourth differentiation rule that we're going to be using to combine together is the sum or difference rule, which I like to combine them together. We have two functions, f of x and g of x, and we can either add them or subtract them. That's the sum and difference. And here, if we're differentiating a sum or difference, we just differentiate each function individually and then add or subtract depending on what sign and operation we have. All right, now typically, as you're going through problems on your own, you're probably not going to apply these and write them out. But for right now, in the first part of the video, let's just make sure you understand how these rules, these basic differentiation rules, go into differentiating a polynomial. In the second part, right after this, we'll get to the more streamlined way to calculate derivatives of polynomials. All right, now our first example, let's differentiate not just a power of x, but let's suppose we have a power of x multiplied by a coefficient, by a constant 3. Now that's going to be one term of perhaps several in a polynomial. So again, before we move on to harder examples, I always like to make sure my students thoroughly understand the simpler examples. And that's about as simple as it gets for a polynomial. All right, now first, what we're going to do, which again, this is not going to be how we'll write the work moving forward, we can apply the constant multiple rule. I can take that constant multiple 3, because there's an implied multiplication sign there between 3 and x to the 4th. I can pull that out front. So let me go ahead and write what the implementation of the constant multiple rule looks like. I'm going to bring the constant 3 out front, and then we differentiate the function of x. We differentiate x to the 4th. All right, and now notice what we're doing is we're taking something complicated, and this is really not complicated, but we're going to be breaking something complicated into simpler pieces. This is what I call divide and conquer. And here we now have the simpler problem of differentiating this basic power of x. That's where we can apply the power rule. The derivative of x to the 4th, that's going to be 4 x cubed. Now how we account for the coefficient, the constant 3 that we pulled out front, is we just write this back, we carry that down, and we have 3 times that derivative. So 3 times 4x cubed. And with practice, you can just do this all in one step. And if you multiply 3 and 4 there, you'll get the derivative as 12x cubed. All right, again, very simple, but this is how we combine these rules together to differentiate things that are more complicated. All right, next, let's go ahead and again apply all those 4 simpler differentiation rules to this polynomial. Now again, this is not how you're going to write the work moving forward, but I want to do that for this first problem. In the second part, in a few moments, we'll get to the more streamlined way to calculate derivatives. All right, now what we're going to do conceptually, we're going to take this sum and difference of coefficients multiplying to powers of x, and we're going to split that apart. Notice we have a subtraction, an addition, and another subtraction. Let's go ahead and repeatedly apply the sum and difference rule. At the same time, what we can do is apply the constant multiple rule because we have coefficients 5, -8, 2, and 4 multiplying powers of x. So let's write down, combining these rules together, what this looks like. All right, I'm going to bring the 5 in front of the derivative. So we'll get 5 times the derivative of x to the 4th. All right, next I'm going to take the next coefficient, -8, pull that in front of the derivative. So I'll write that as -8 times the derivative of the power of x, x cubed. All right, next I can take the coefficient 2, pull that in front of the derivative. And then we'll be differentiating the power of x, x squared. Next, I'm going to take the coefficient 4, pull that out front, and we're going to differentiate the power of x, which is just x, or x to the 1. All right, and our last term, I'm going to write that as minus. Think of that as -3, as -1 times +3. So you can pull the coefficient of -1 out front, and we're going to differentiate 3. All right, again, this work is tedious, and never write this work moving forward, but it's going to help us understand how we apply these rules to differentiate a polynomial. Now what we're doing here is we're breaking it down to repeated, simpler calculations, and now we can just apply the power rule and the derivative of a constant rule. So let's just go ahead and write the work out. The derivative of x to the 4th, that's going to be 4x cubed. All right, the derivative of x cubed, that'll be 3x squared, applying the power rule. All right, next simple calculation, the derivative of x squared. That's going to come out to 2x, or 2 times x to the 1. Next, the derivative of x, and make sure you think of that as x to the 1st power. We saw that in an earlier video, linked down below in the description, so check that out if you're not sure. The derivative of x, applying the power rule, bring the power 1 down and subtract 1 from the exponent, you'll get x to the 0. The derivative of x, that comes out to 1. And the final simple or easy calculation, the derivative of a constant, the derivative of any constant, the derivative of any number, that's going to be 0. All right, and the only thing we need to account for now are the coefficients or constants that we pulled out front. And again, you're probably okay combining all these steps together, but I'm not going to assume that. Again, I want to make sure you're learning as much as possible. So now let's go ahead and multiply 5 to 4x cubed. And if you multiply there, that's going to come out to 20x cubed. Next, we have our coefficient that we pulled out front, -8 times 3x squared. We can write that as -24 x squared. Here, we're going to multiply and get 4x. Here, we're going to multiply and get just 4 times 1. And just for emphasis, I'm going to write minus 0, reminding ourselves that when we differentiate a constant, that derivative is 0. And there we go. That is conceptually how we apply all these differentiation rules together to calculate the derivative of a polynomial. Now again, this work here is very tedious, and do not write that work moving forward. What you want to get comfortable with is how to go from the original derivative that you're calculating here. You want to be able to go straight to there in your head, or conceptually applying all these rules together without having to write all that work down for the individual steps. All right, now if you're ready, let's go ahead and get to some more examples right now. Next up, we're going to take a look at 3 examples. The first one is very straightforward, and what we're not going to do is write down all the work like we did in the previous part. But we're still going to apply the differentiation rules, but try to incorporate some of those steps all together. Now, what we're going to notice is we have coefficients multiplying powers of x that we're adding and subtracting together. So we're going to basically apply the constant multiple rule, the power rule, and the sum and difference rule all together. And here is how you probably want to write your work, just to make the problems as efficient as possible moving forward through your Calculus 1 course. So here our function is called f of x. The derivative, we're going to write that as f prime of x. And because we're subtracting and adding, we're going to differentiate term by term. So your first term, we have a constant 4 multiplying a power of x. We can take that constant, or constant multiple, and multiply that to the derivative of the power of x. So here we're going to have 4 times the derivative of x cubed, and that with the power rule comes out to 3x squared. All right, next term, we have a constant, -6, and that's going to multiply the derivative of x squared, which is 2x. Next, we have the term 5x. We have a coefficient of 5, and that will multiply the derivative of x. Think of x as x to the first power, and we've done this several times already. The derivative of x is 1. And your last term, 2, notice there is no x multiplying that, so we're going to think of 2 as a constant. The derivative of any constant is 0. So we're just going to write plus 0 at the end here. And you might have already done some simplification as you went through this, but we're easing into this. So now you can just go ahead and combine some of those numbers together, and it looks like we're going to get 12x squared minus 12x plus 5. And that's pretty standard and efficient work at this point in Calculus 1. And again, you'll want to be comfortable doing that just to make the problems go as fast as possible, because you're going to be applying derivatives to more complicated problems a little bit later in your Calculus 1 course. All right, next example, 2. First, we change the variable from x to t. Again, we're just going to make sure you're comfortable with that. And that shouldn't be the complicated part here. All right, but what we're going to notice is we have something with powers of x written in factored form. Now there is a rule that you'll learn later in your Calculus 1 course for this called the chain rule, but we are not thinking of that yet. We don't have access to it. Now we can use one of the more basic ideas. Here we can just rewrite this, and that's going to allow us to differentiate things in as simple a way as possible. So rewrite before you differentiate. And here we can just rewrite that by expanding, multiplying, or foiling. So we're going to think of that as 2t plus 3 times itself, 2t plus 3. And if you just go ahead and multiply that out, looks like what you should get for s of t. First terms are going to multiply to 4t squared. All right, your outers will give 6t. Your inners will give another 6t. That'll come out to 12t. And then your last terms multiply to 9. And at this point, once we rewrote our function, so rewrite before you differentiate, now we have it in the form of a basic polynomial, but now the variable's t. All your rules still apply, all the work is the same, we're just differentiating with the variable t. So we have our function s of t, and let's go ahead and write down the derivative, and we're going to go through the work exactly like we did here. We have a coefficient 4, and that's going to multiply the derivative of t squared, which would be 2t. All right, next we have a coefficient 12, and now we're differentiating t, or t to the first power. That is exactly like the derivative of x, which is 1. The derivative of t is also 1. And your last term, like above, the last term is again a constant. The derivative of any constant is 0. All right, we can just clean that up. Looks like we can write the first term there as 8t and then plus 12. And by rewriting it, it was very quick to differentiate it. All right, now so far, these two examples were polynomials. The first one was obviously written as a polynomial, and here we had a polynomial in factored form. Your third example technically is not a polynomial because we're dividing, but if we rewrite this, we can differentiate it exactly the same way like we would differentiate here. We're going to try to rewrite the function in example 3 as a bunch of powers of x, and we're going to allow for negative powers. This is a very important technique. If you know the quotient rule, you might be tempted to apply that, but you do not have to here. We're going to rewrite it first. So what we're going to notice is we're dividing by x squared, a single term. I can take each term in the numerator and divide it by x squared. Let's go ahead and write that out. We're going to have x cubed divided by x squared. We're going to have minus 5x squared divided by x squared, and then your last term, 2, we're going to divide that by x squared as well. All right, go ahead and simplify this. We're not differentiating yet. Your first term, you can rewrite that as x. In the middle, the x squareds cancel completely. We can write that after simplifying as minus 5. And the last term, 2 over x squared, we're going to rewrite that as a power. And what we're going to be using is 1 over x squared. We can rewrite that as a negative power, x to the negative 2. And that's a very common trick or technique that you'll want to be comfortable with. All right, so your last term here, I'm going to write that as plus 2 times x to the negative 2. All right, and it's important to mention that this is not a polynomial. Polynomials have to have powers of x raised to positive integer powers. And here we have a negative power, so that's automatically not a polynomial, but it differentiates the same way. All right, now let's go ahead and differentiate this. Our function is g of x. So we're going to call the derivative g prime of x. And now we can just differentiate that term by term. All right, let's take it one term at a time. The derivative of x, we've done that several times. That derivative comes out to 1. 5, that's a constant, that differentiates to 0. And your last term, that's where we have a constant multiple, so we'll write plus 2, and then times the derivative of x to the negative 2. And since the power is negative, let me go ahead and use a set of parentheses. So we're going to write this as plus 2 times, now we differentiate using the power rule, x to the negative 2, we bring the power down, and subtract 1 from that exponent. So the derivative of x to the negative 2, we get it as negative 2 times x to the negative 3rd power. And from here we can simplify. We have, for the first term, 1. We don't need the minus 0. But notice here we can multiply and get negative 4 times x to the negative 3rd power. Now moving forward, you'll want to be comfortable simplifying or rewriting your derivative for various reasons. And here I can rewrite this back as a fraction. X to the negative 3rd, I'm going to rewrite that as 1 over x cubed. So we're just using that basic rule relating reciprocals and negative exponents together here. I'm going to rewrite this last term as 1 minus 4 over x cubed. And there we go. Again, technically here, the function g of x is not a polynomial, but it differentiates exactly the same way. And these two examples, example 3 and example 2, illustrate an important tip. Rewrite before you differentiate. And we're going to continue to mention that as we get to harder problems involving more differentiation rules. Hope you enjoyed the video. If you did, support the channel, like and subscribe.